let's now put this all together and see what the mathematics here is trying to tell us. Let us now interpret the behavior of the circuit. Now, remember, what happens is that we take this particular circuit and we hook it up to an AC drive. And what we're asking is, for a given amount of input, right, what then is the current response? That's what I0 is telling us. It's telling us the amplitude of the current response, and the phase phi is telling us the relationship between when we have a maximum input voltage and when we have a maximum response current. So really the question that we have answered is, what happens to how does the current behave? So this is the current behavior. Now, the simplest thing to ask about is, well, how does the current behave? We know that the current is going to be some kind of oscillatory function with a certain amplitude. And the easiest thing to try to understand is how the amplitude of the current corresponds to the amplitude of the input voltage signal. And that is determined by our function here. So it's helpful to make a sketch then of that behavior. So I'm going to plot then the amount of current response I0 that I get, the I0 amplitude, as a function, say, of the frequency. And we find something very interesting, actually. This function, notice, has a well-defined maximum value, right? The maximum current I can get out is, of course, when the denominator is a minimum for a given input voltage. And the denominator is a minimum when this factor here actually has the value of 0. That's the least I can have for the denominator. When this factor is 0, notice that at that particular frequency, the current will just be the EMF divided by root r squared, which means it's EMF divided by r. So there's a certain frequency here where I get the maximum value. I will call that frequency omega naught. And the value that I get happens to be the EMF, the input EMF amplitude, E naught, divided by the resistance. And that's then the maximum value that I will find. Now, it occurs when these two factors are in direct alignment. That happens then when 1 over omega naught C equals the other factor of L times omega naught, which we can solve. We bring the L onto this side of the equation where it goes on the bottom, 1 over LC. I bring omega naught over here, so I have omega naught squared is 1 over LC. In other words, omega naught is the square root of 1 over LC. And that, in fact, is the natural period of oscillation of what's called an LC circuit when there's 0 resistance in the circuit. So we're going to have this maximum value there. Now, you'll notice that I've drawn this maximum function as a very narrow maximum, where it's going to drop down fairly quickly. That is the case, actually, when we put a very small resistance into the circuit. And we will explore that in a little more depth coming up in just a moment. That'll be the last thing that we will discuss in the lecture, is the width of this peak. I'd like you to also notice what happens at low frequencies and at high frequencies. At very low frequencies, 1 over omega c dominates the term on the bottom. And then when I square it and take the square root, I have E naught over 1 over omega c, or I just have omega c e, which is then just linearly proportional to omega. So down here we have this range behavior where I just have omega times CE, which C times the EMF amplitude. And this is a regime where we are dominated then by the capacitor. This is capacitor dominated. At very high frequencies, the denominator then is dominated by the L times omega term, which when squared and square rooted just gives me L omega. So I have something that is going like 1 over frequency out here. So there's a decay towards 0 right down here. And out here the behavior is E naught over L times omega. And this regime is, instead of being capacitor dominated, this is the regime which is the inductor dominated. Finally, we had that intermediate regime. And notice, in the intermediate regime, the behavior is just what we would expect if we just had a resistor and our EMF, right? The inductor and capacitor terms are canceling out. I just have I equals E over R, which is what I expect actually if I am controlled entirely by the resistor. So there's this resistance-dominated regime when I'm very, very close to that frequency of omega naught. So that's the current behavior, and these then curves have to somehow, line up together, something like that. That's the amplitude behavior. Then we have the phase, and I wanted to think a little bit carefully here about the phase. When I think about the phase, notice that the way we've defined things, for a positive phase, the EMF hits its maximum after the current hits its maximum, right? So this would say that the EMF is what we call phase delayed relative to the current because the phase maximum happens after that of the current. Typically, we're more interested, right? We're interested in the current response. We want to know what the current's behavior is relative to the driving EMF. In this case, as drawn, when phi is positive, the current actually has its phase, its maximum happens before that of the EMF. That we call a phase advance of the current over that of the EMF. So phi is actually telling us the amount of this phase advance of the current. So I can make a plot of that as well. This would be the phase advance of I versus the EMF. Now that function, if I were to plot it, actually can be either positive or negative as a function of frequency. Here's my function. Notice that at high frequencies, I am dominated by the L omega term, and I will have the arctan then of a very large negative number, and the arctangent of infinity is pi over 2, but when omega is large, I'm getting a negative very large number, so I have to approach minus pi over 2. So the phase advance goes to minus pi over 2 for very large frequencies, which is another way of saying, since this is negative, this actually means that there is a phase lag as the frequency goes to infinity. When frequency goes to 0, and I consider my function, and once again, notice, at these high frequencies, the term which dominated again was the inductor. So again, I'm inductor dominated out here. At low frequencies, when omega goes to 0, it's this first term that dominates. I get a positive infinity. The arctan of a positive infinity then is pi over 2. So the phase should, at the beginning, be positive like so. And the phase actually will cross through 0. And it's interesting because if you look at where the phase goes through 0, if I want arctan of 0 to give me a 0 angle, I need these two terms to subtract to give me perfectly 0. But those are precisely the same two terms which determined the maximum frequency response. So it actually goes through 0 at omega naught, which is then that one point which is, again, resistor dominated. So notice again that for high frequencies, this was the L dominated regime. Over here, I had the capacitor dominated, C dominated. And at this point, everything is controlled again by the resistance, R dominated. And notice, when I have just a resistor in a circuit like this, right, when it's just the resistor, I know that the current flowing through just a resistor will be positive when the voltage is positive and negative when the voltage is negative. I should have no phase shift between current and voltage when I'm controlled purely by the resistor. and indeed that's what we are finding. That's the point where we cross at omega naught.